Hello and welcome. You've found your way to our refuge, where we welcome the great and beautiful ideas of the universe and gently unravel them in a slow, calm and soft manner, just enough to lull you to sleep. Whether it's to relax after a long day or simply to satisfy your curiosity about the cosmos from the comfort of your pillow, I'm glad you're here. I really hope this video isn't so interesting that it keeps you wide awake. But if that's the case, at least you'll wake up a little wiser than you were before falling asleep. If you enjoy this journey through science for sleep, it would mean a lot if you gently hit the like button and maybe even float over to subscribe. It helps this little channel grow and reach more minds passionate about science, just like yours. And while you're still awake, feel free to tell me where you're listening from and what time it is in your part of the world. I always love seeing how many corners of this spinning planet we've reached. Now then, fluff your pillow, adjust your blanket, and settle in. We're about to follow the curves of the cosmos together. And just a gentle reminder, this video is for educational and relaxation purposes only. It is not medical advice or a substitute for professional care. They say the shortest distance between 2 points is a straight line, but in this curved, spiraled, and quietly complicated universe, that idea rarely holds. Even the straightest path, when drawn over a long enough distance, begins to curve. A beam of light bends as it passes a massive star. A migratory bird follows the arc of the Earth's surface. A river left to its own devices meanders back and forth with a kind of lazy perfection. Around us, the world seems to prefer loops over lines, spirals over spears, smooth curves over direct routes. So, it's worth asking, when you're preparing for the night, do straight lines really exist in nature, or are they just something we've invented? Perhaps they are merely an idea, an ideal that exists more comfortably in minds and mathematics than in the mud, sky, or stars. In this video, we will take a slow walk through that question. We'll explore why the universe seems to bend almost everything it touches. Why galaxies spin like vast hurricanes. Why blood vessels intertwine in our bodies in branched arcs. Why space itself, something we often imagine as flat and empty, bends under the weight of matter, bending time along with it. And even down to the tiniest scales, particles seem to prefer dancing in clouds over marching in rows. This isn't just a story about shapes. It's a story about how the universe moves, grows, and breathes. It's about how life evolved to fit in a curving world. It's about how geometry isn't just a book of rules, it's a language, and it speaks in curves. There's no need to rush. We're not here to seek answers. This journey isn't about memorizing facts or formulas. It's about floating gently from one idea to another, letting them settle like snowflakes or spiral like seeds. If you fall asleep at some point along the way, that's okay. The curves will still be waiting when you wake up. So tonight, we're leaving the straight path behind. We're leaving behind our rulers, our right angles, and our grids. And stepping into a softer geometry, the kind that shapes galaxies and tree branches, blood vessels and orbits, paths of light and time itself. Let's see where the curves lead us. The straight line is one of humanity's longest-lasting inventions. You'll find it in ancient temples and new skyscrapers, in the grid streets of cities and the ruled pages of notebooks. It's the backbone of designs, the guide for engineers, the mark of precision. We silently venerate it, perhaps without even realizing it. Every time we admire a neatly trimmed lawn or a well-paved road, Every time we draw a line between two ideas and call it logic, the truth is, the straight line is less a feature of nature and more a product of our imagination. Euclid, the ancient Greek mathematician, was one of the first to formalize it. He described the straight line as a length without thickness, infinitely thin, extending forever in both directions, perfectly straight, perfectly smooth. It's a beautiful concept, clean, simple, reliable, but it lives in a world of thought, not soil or sky. In the real world, things are messier. Try to find a truly straight line in nature, and you'll search for a long time. Trees grow toward the sun in soft arcs. Rivers meander and wander to the horizon, which looks flat at first glance. It curves. If you follow it for a long enough distance, the mountains rise, the coastlines fade, the clouds swell. Nature rarely deals with sharp angles or unshakable paths. Still, we are drawn to straightness. There's something comforting about it, something efficient. Draw a straight road through a forest, and you've imposed order on wild nature. Lay out a rectangular garden, and you've tamed the wild into a pattern. Humans have always tried to straighten what was never straight. For starters, we've dug tunnels through mountains. Instead of going around them, we've stretched bridges over rivers. Rather than let the path follow the edge, we've gridded our cities, boxed in our houses, framed our paintings. The more we build, the straighter our surroundings seem to become. Maps are a wonderful example of this. We flatten a round planet onto a sheet of paper and draw straight lines between destinations. But those lines are straight only in appearance. On the globe itself, the shortest path between 2 points is actually curved. It's called a great circle. Planes follow these arcs all the time. Even though the line seems crooked on a two-dimensional map, our eyes see a curve, but mathematics says it's the shortest distance. Even the tools we use to define straightness are imperfect. A ruler, no matter how finely crafted, can warp over time. A laser pointer will eventually deviate slightly over long distances. Due to refraction or interference, the materials we build with, wood, metal, stone, expand and contract with temperature, humidity, and age. Nothing stays perfectly straight for long. In our minds, however, the straight line has power. It represents clarity, purpose, and decisiveness. A straight line is a path without hesitation. That's probably why we favor it so much in design. Straight lines seem deliberate. They imply control. Architects use them to convey order. Graphic designers lean on them to create balance. Even language borrows the metaphor. Someone who tells the truth is considered straightforward, while someone untrustworthy might be called crooked. But nature doesn't care about our metaphors. Nature, if anything, is playful. It curves not out of laziness, but because curves are often more efficient, more stable, and more adaptable. A straight tree branch breaks in the wind. A curved one bends and survives. A straight river cuts too deep and too fast, eroding its banks. A curved river flows with less violence, spreading its energy gently. Curves distribute stress more evenly. They allow movement, growth, and resilience. Our brains also seem to prefer curves. Psychological studies have shown that people tend to find curved shapes more pleasant, more natural, and even more calming than angular ones. One theory is that sharp angles may unconsciously trigger a sense of threat. After all, sharpness often means danger. Curves, on the other hand, seem safe. They're the shapes of rolling hills, rounded stones, and flowing water. They invite us in rather than push us away. Still, we cling to straight lines. They help us measure, define, and build. They give us grids to navigate, charts to interpret, and structures to organize our thoughts. Without them, modern life would be very different. But by relying on them so heavily, we sometimes forget that they are just approximations. Zoom in close enough, and even a laser beam wobbles. Zoom out enough, and even a highway begins to curve with the Earth. The straight line is a tool, a useful one, no doubt, but it's not nature's native language. It's a translation, a simplification of a world that is much more fluid than we tend to admit. A world that doesn't march, but flows, that doesn't cut, but undulates. It's a reminder that our best ideas, even the cleanest ones, are just that: ideas, models, convenient ways of making sense of a universe that resists simplification. And maybe that resistance is the most beautiful part when you look at the night sky. It's easy to imagine space as a vast empty stage, a smooth, infinite canvas stretched in all directions, with planets and stars floating silently through it like actors in a slow-motion ballet. For centuries, that's more or less how people thought of space: flat, passive, and silently complacent. But space, as it turns out, is anything but flat. It bends, undulates, warps, and stretches like a soft fabric under tension. And once you realize that, nothing in the universe seems quite the same. This idea, the shape of space, is one of the most quietly revolutionary realizations in all of science. We owe much of it to Albert Einstein, whose general theory of relativity, published in the early 20th century, changed our understanding of space from a rigid backdrop to a flexible participant in the drama of the universe. According to Einstein, gravity isn't a force pulling objects toward each other like invisible strings. Instead, it's the result of mass and energy curving the fabric of space-time. Imagine a rubber sheet stretched tightly. If you place a heavy bowling ball in the center, the sheet will curve under its weight. Now roll a smaller ball across the surface. Instead of moving in a straight line, it describes an inward arc captured by the depression created by the bowling ball. It's not that the smaller ball is being pulled, it's simply following the curved shape of the sheet. In this metaphor, the rubber sheet is space-time, the bowling ball is a planet or a star, and the small ball is another object, perhaps a satellite or even a beam of light, moving along the curves created by gravity. That's what Einstein proposed, that objects move not because they're being pulled, but because they're following the geometry of space itself. It's a simple idea, and yet its consequences are profound. Gravity is no longer a mysterious force, it's geometry, and space isn't the silent, motionless stage we once imagined it to be. It's dynamic, responsive, and strangely alive. Earth, for example, isn't being pulled toward the sun like a stone on a string. Instead, it's moving along a curved path in space-time, distorted by the sun. It's not that gravity extends and pulls the planet. It's that Earth is falling around the sun, endlessly trapped in the curvature created by the sun's mass, like a small ball circling forever in a funnel, never falling all the way in, but also never escaping. This idea isn't just theoretical, it's been confirmed time and time again. One of the first pieces of evidence came in the form of starlight. During a solar eclipse in 1919, astronomers observed that stars near the edge of the sun were slightly displaced from their expected positions. The reason? Their light had been curved as it passed through the sun's gravitational well, It was one of the first direct confirmations of Einstein's theory, and it caused quite a stir at the time. Headlines couldn't contain it. Einstein had toppled Newton. Of course, Newton wasn't exactly wrong. His laws still describe how gravity behaves in most situations, especially at everyday speeds and scales. But they didn't explain why gravity works. Einstein explained, and his version of the universe was much more curved. To imagine space more accurately, it helps to think of it not as flat terrain, but as an invisible fabric, something soft, stretchy, and three-dimensional. Objects with mass sink into this fabric, creating depressions or wells that affect how other objects move nearby. The more massive the object, the deeper the well. A tiny rock barely dents the fabric. A planet makes a decent-sized hole. A black hole? That's a tear without end. Even light, traveling at the fastest speed possible, isn't immune to this curvature. When a beam of light passes near a massive object, its path curves, not because it slows down, but because the space it's traveling through is curved. The light ends up tracing an arc. This effect, known as gravitational lensing, allows astronomers to detect galaxies that are behind other galaxies. The light curves around the mass in the foreground, like water around a stone, and creates magnified and distorted images of things that would otherwise remain hidden. There's something poetic in that. Light, often our most straight symbol, our beam of truth and clarity, curved by the very fabric of existence. It reminds us that even our simplest metaphors have their limits. Another helpful way to visualize this is to imagine a ripple spreading across a lake. If the surface is smooth, the ripple moves uniformly in all directions. But if there's a large rock in the water, the shape of the ripple changes as it goes around it. That's how space behaves when mass or energy is introduced. The presence of something heavy distorts the surrounding space and anything that moves through it. Ripples, marbles, planets, photons. It follows the new curved geometry all the way to time. It's part of that dance. According to general relativity, space and time are intertwined into a single entity, space-time. When space curves, time curves with it. That's why time passes a little faster on the GPS satellites that orbit above Earth than it does on the ground. They're farther from the planet's mass, on a gentler slope in the gravitational well, and time runs a little differently up there. This isn't science fiction, it's scientific fact. Engineers need to account for these differences when programming the clocks on the satellites, or else their directions to the supermarket could be off by several kilometers. All of this leads to a subtle but crucial realization. The universe doesn't operate on a flat playing field. Its rules are curved, its paths winding, and its movements, when observed closely, reveal the silent elasticity of everything. Mass tells space how to curve, and space tells mass how to move. It's not a tug of war, it's choreography. Once you start seeing things this way, it's hard not to see it everywhere. Planets aren't just spinning, they're tracing elegant arcs in an invisible, distorted sea. Light isn't just shooting forward like a laser pointer in the dark. The idea of a perfectly straight path starts to appear more as a myth than a measure. And maybe that's what makes it so quietly amazing. Even emptiness curves. There's a certain elegance in the way things move through space. A moon orbiting a planet spinning around a star, a star sliding along the arm of a galaxy spiral. None of them travel in a straight line, at least not for long. Instead, they curve, spin, and fall along paths shaped by the gentle pull of gravity. It may seem like an object moving through space should go straight, unless something gets in its way. That's not a bad instinct. It's part of what Isaac Newton figured out centuries ago. He told us that an object in motion stays in motion in a straight line unless a force acts on it. But gravity is always acting, and that's where the curves begin. Imagine firing a cannonball off a cliff. Fire it gently, and it falls just below. Fire it with more force, and it travels farther before hitting the ground. But if you could fire it fast enough, its curve would match the curve of the Earth. It would never hit the ground. It would keep falling forever, but always missing it by a little bit. That's what an orbit is, a controlled fall. The object isn't flying straight, it's curving around something, trapped in a constant balance between its momentum and the gravity pulling it inward. This idea fascinated early astronomers. Johannes Kepler, working in the early 1600s, spent years studying the paths of the planets. He discovered that they didn't move in perfect circles, as people had long assumed, but in ellipses, gently stretched loops. Each planet traces an oval path with the Sun not at the center, but slightly off to the side. In one of the two foci of the ellipse, that was a revelation. It showed that celestial motion wasn't based on ideal symmetry, but on a more flexible, precise form. Kepler didn't know why the planets moved this way. He simply described what he saw with mathematical accuracy. It wasn't until Newton came along that a deeper explanation emerged. Newton's law of universal gravitation explained how two objects attract each other with a force that decreases with the square of the distance between them. Combine that with his laws of motion, and suddenly Kepler's ellipses made perfect sense. A planet's orbital curve is the exact result of its speed and the gravitational pull of the star it orbits. If gravity were turned off, a planet would shoot off in a straight line, flying through space forever, but gravity keeps it nearby, curving its path like a hand guiding a marble around the edge of a bowl. That balance between motion and attraction is what allows orbits to exist, not just for planets, but for moons, satellites, and even space probes. The International Space Station, for example, isn't hovering above Earth. It's falling around it, again and again, traveling at over 17,000 miles per hour. There's nothing pushing it forward. It's simply gliding along its curved path, high and fast enough to stay in free fall, gracefully. These curved movements don't just belong to perfect loops. Depending on speed and angle, an object can enter a wide variety of orbital paths, some tight and fast, others long and slow. A comet, for example, may come from the outer reaches of the solar system, trace a stretched elliptical loop around the sun, and then be thrown back into the void for hundreds of years before returning. It's still orbiting, but in a much more dramatic way. There are even hyperbolic and parabolic trajectories, curves that don't come back. These are the paths taken by objects that move fast enough to escape a gravitational pull entirely. A spacecraft performing a slingshot maneuver passes by a planet, using its gravity to redirect its path without falling into a closed orbit. Again, it's not moving in a straight line. It's tracing a curved exit route sculpted by the planet's gravity that it's escaping. Even within the apparent simplicity of an orbit, the path is rarely constant. The Moon's orbit around Earth wobbles slightly. Earth's orbit around the Sun changes shape over long timescales. These variations, called orbital perturbations, arise from the gravitational pushes of other nearby bodies. Jupiter, for instance, has a strong influence on the paths of many objects in the solar system simply because of its massive size. And then, the fact that orbits don't happen in isolation. The Moon orbits the Earth, which orbits the Sun, which orbits the center of the mill.
you.